Welcome to today's Explainer. All right, let's jump right in, shall we? If you're an electrical engineer stepping into an interview room, or honestly, just walking onto an industrial floor for the first time, there is a golden rule you've got to memorize right now. Ditch the dense college textbooks. Seriously, when a senior engineer asks you a practical question, they do not want a 20-minute lecture. No way. They want you to deliver your answer in just 3 to 4 concise sentences. You need to prove you know how things actually work in the real world. So today, we're breaking down some fantastic insights straight from expert industrial practices to give you exactly those winning, to-the-point answers about the absolute workhorse of the industry, the induction motor.
Here's our roadmap for today. We're going to cover 1. The basics, 2. Speed variation, 3. Induction versus synchronous motors, and finally, 4. The self-starting mystery. By the end of this, you'll have mastered the 4 most common practical scenarios you're going to face out there.
Section 1. The Basics. Core Motor Concepts.
So picture this. You're sitting across from the interview board, sweating a little bit maybe, and they drop this classic question on you. What is an induction motor, and how is it different from the rest? Now, like we just talked about, do not recite a whole chapter. Take a breath. Just simply state that at its core, it's a machine that converts electrical energy into mechanical energy. And crucially, you've got to add that it is absolutely the most common motor used across all modern industries. It's literally the backbone of the factory floor. But to really nail how it's different, we need to talk about its specific traits.
I mean, why does the industry just love this motor? Well, first off, it has this incredibly simple and robust construction. I mean, it is built like a tank. And because of that, it's highly maintenance-free, which, as you can imagine, saves companies massive amounts of downtime and money. It's a real game changer. Third, it allows for easy speed variation, giving it incredible flexibility. Then you just wrap up your answer by mentioning how it's classified. It's divided into 1-phase and 3-phase categories, with the 3-phase being further split into squirrel cage and slip ring forms. Boom! That perfectly summarizes its robust nature and speed flexibility, proving exactly why it is the reigning undisputed champion of industrial motors.
All right, moving on to Section 2. Speed variation, controlling RPM.
Now, pay attention here, because the word practically is the trap. They're going to ask, how do you practically vary the speed of an induction motor? The crucial thing to remember is that you have to pivot the conversation toward the specific starting methods used to alter that RPM. You can't just ramble about the theory of speed, right? You actually have to talk about the physical hardware on the floor that makes it happen.
So to answer this effectively, you kind of want to illustrate the evolution of control. You start by acknowledging that direct online, or DOL, and star-delta starters are your standard starting methods. But if you want to achieve true RPM variation, you absolutely have to implement a variable frequency drive, commonly known as a VFD. You tell your interviewer that by slapping a VFD on there, you can easily ramp the RPM up or down exactly according to whatever the industrial requirement is. Hitting them with this shows you understand not just how a motor starts, but how it's dynamically controlled in a modern, real-world plant.
Next up, Section 3. Induction versus synchronous, the industrial rivalry.
This is a classic one. Why do industries heavily favor induction motors over synchronous motors? It's such a great question. To craft that perfect, concise answer, you've got to confidently explain the physics behind the rotating magnetic field. But hey, don't worry, we are going to keep the math incredibly simple and highly effective here. Okay, synchronous speed. The formula is NS equals 120F over P. Now, seriously, don't let those letters intimidate you. All this formula is doing is representing the theoretical speed limit of the motor's magnetic field. That's it. It is the exact, precise speed at which the motor's rotating magnetic field travels. And once you lay this out for the interviewer, you have basically set the perfect trap to explain the real difference between the two motors.
You just synthesize it like this. An induction motor always runs slightly below synchronous speed. But because of this tiny lag, it offers highly flexible speed variation, especially when you pair it up with that variable frequency drive we just talked about. On the flip side, the synchronous motor, well, it's pretty stubborn. It runs exactly at its rated synchronous speed, or it just doesn't run at all. Zero flexibility. None. So your final winning sentence to the interviewer is this. Industries favor induction motors because their flexibility allows us to adapt to different loads, whereas the synchronous motor's rigid nature gives us absolutely no speed variation options. Hit the nail right on the head.
Finally, Section 4, the self-starting mystery, 1-phase versus 3-phase.
Why is a 3-phase motor self-starting, but a 1-phase is not? Man, this specific question trips up so many candidates. They just get totally lost in the weeds of complex electrical theory. But the secret to answering this clearly and concisely?
It lies entirely in identifying the type of magnetic field being produced by the supply.
Check this out. When you apply a three-phase supply, it produces a magnetic field that naturally rotates, and that creates a rotating torque, making it effortlessly self-starting. But a one-phase supply? It produces an alternating magnetic field. This means for one half cycle it pushes clockwise, and then for the very next half cycle it pushes anti-clockwise. It's basically playing tug-of-war with itself. It effectively cancels itself out, resulting in a net torque of absolute zero. It just sits there, stuck, totally unable to start.
Now, if you really want to knock their socks off, ground this heavy theory in an everyday analogy. Just point out that this is exactly why household ceiling fans, which run on a single phase by the way, need a capacitor. That capacitor acts like an artificial extra phase. It creates a phase shift which provides that necessary initial rotational push to overcome the zero net torque. Just like that, you've brought some pretty complex physics right into the interviewer's living room.
And there you have it. You now know the theory, but way more importantly, you know exactly how to communicate it. I strongly encourage you to keep these precise, practical, 4-sentence answers ready in your back pocket at all times. By focusing on the practical reality rather than all that textbook fluff, you can confidently step onto any industrial floor or into any high-stakes interview. Which leaves us with one final thought to ponder today. If our mastery of these invisible magnetic fields currently runs basically the entire industrial world, what kind of unseen physical forces will we be harnessing to power the industries of tomorrow? Keep learning, keep questioning, and I'll catch you in the next explainer.